Large language models can continue prose, translate, write code, and answer in many styles. Their engineering is enormous, but the statistical contract at the center of language model pre-training is familiar. Given the tokens already present, assign probabilities to what comes next. Then reward the probability assigned to the token that actually occurred. Here is one public scale marker. Meta's largest Llama 3.1 model had 405 billion parameters and was trained on more than 15 trillion tokens. Almost every token position becomes a prediction target. One corpus can therefore create trillions of conditional likelihood contributions. Scale changes the engineering, the computation. And what the fitted system can do, it does not change the core statistical object. A model supplies conditional probabilities. The corpus supplies observations. Likelihood scores the observed next tokens. Optimization adjusts the weights. This is likelihood machinery at language model scale. A coin model assigns probability to two possible outcomes. Once heads is observed, its probability becomes one likelihood contribution. At a language model position, replace those two outcomes with every token in the vocabulary. The statistical move is unchanged. Only the number of alternatives has exploded. The context and the weights, called theta, produce one logit for each possible token. Softmax raises e to each logit and normalizes the results, turning them into probabilities that sum to 1. A real vocabulary may contain tens of thousands or even hundreds of thousands of tokens, depending on the model. The corpus reveals which token actually came next. That observed token selects one probability from the entire distribution. Change the preceding context and every logit may move, so the distribution reshapes. This is a very large conditional categorical model, probability of a token, given its context and the weights. Suppose the corpus contains the sentence shown on screen. At each position, the model sees the actual earlier tokens and assigns probability to the actual next token.
Is it feeding back its own predicted token during training?
Not in standard next token pre-training. The corpus supplies the context. This is often called teacher forcing. At the first marked position, one context produces one observed target and one conditional probability. Move right and the context grows. A new target produces a new contribution. Move again. One sequence therefore supplies many related training examples, one for nearly every token position. The probability of the complete sequence factors into the product of those next token probabilities. This is the chain rule. Not an approximation. The autoregressive model specifies how each conditional distribution depends on the context. Taking logs converts the product into a sum, which is far easier to accumulate and optimize. During generation, the model samples or chooses a token and feeds that output back into the next context. During teacher-forced pre-training, the corpus supplies the next context. The behaviors differ, but the learned conditional probabilities are the bridge between them. Training dashboards usually say cross-entropy, not likelihood. Are these different objectives? For a categorical next token target, they are the same calculation viewed from opposite directions. Represent the observed token by a one-hot target distribution, 1 at the token that occurred and 0 everywhere else. Categorical cross-entropy multiplies each target entry by the log of its predicted probability. Every 0 term vanishes, leaving only negative log probability of the observed token. When the observed token receives probability 0.8, the loss is about 0.22. When it receives probability 0.05, the loss is about 3. The logarithm gives a large penalty to a confident, wrong prediction. Average this quantity over token positions, and minimizing the loss is exactly maximizing average next token log likelihood. Exponentiating the average cross-entropy gives perplexity, a common language model metric. Lower held-out perplexity means the model assigned more probability to the tokens that actually appeared. Compare perplexities only when the evaluation data and tokenization are the same. A corpus with trillions of token positions is too large to revisit in full before every weight update. Instead, Select a mini batch of sequences or token positions, compute their average loss, and backpropagate its gradient. It is simply a smaller batch of training examples. Under uniform sampling, the mini batch gradient is a noisy but unbiased estimate of the full corpus gradient. One batch suggests one update direction. A new batch suggests a slightly different direction. Repeating this process lets the optimizer make progress without evaluating every contribution at every step. Many devices can process different mini batches in parallel and combine their gradients. That is a computational strategy. The objective remains average next token negative log likelihood. Likelihood defines what counts as fit. Stochastic optimization defines how the search proceeds. It still does not prove a unique global optimum. Lower training loss means a better fit to the training corpus. It does not by itself guarantee factuality, calibration, or better behavior on unseen text. Validation loss asks a different question. Does the fitted conditional model continue to assign high probability beyond the observations used to fit it? Next token pre-training builds a base model. Instruction tuning, preference optimization, tool use training, and safety work introduce later datasets and sometimes different objectives. Those stages matter enormously. We should not attribute every final behavior to maximum likelihood on the original corpus. Standard pre-training retains one fitted weight configuration. A full Bayesian posterior across billions of weights would quantify a different kind of uncertainty and is far more computationally demanding. Ordinary cross-entropy training does not compute that posterior. Now every box in the playlist pipeline has a concrete meaning. The transformer and its weights define the model. The tokenized corpus supplies observations. Next token likelihood scores them. The optimizer uses small batches to scale the search. Held-out evaluation probes what the fitted model did not guarantee. A language model is far more than a loss function, but its central pre-training objective is maximum likelihood, written as cross-entropy at extraordinary scale.